So what we want to do now is we said we can actually plot and look at our concentration dependence for our reactants versus time for our different orders of reactions by integrating the different rate laws. So the one we did first was zero order, and we saw that it's a linear decay, okay? So for first and second order, it is not linear. But it's still relatively simple integration. If I can do it, you can do it. All right, so let's integrate our first order reaction. Okay. So this was our case where we just have A turning into product. Okay. And we can write our reaction rate, dA dt, is equal to negative K, our rate constant. Always positive. The negative is here because we have a loss in the concentration of A. So we can rearrange this. Okay, let's get temp on the right side, and we'll divide concentration of A over. And so what we'll have is 1 over the concentration of reactant A, dA, is equal to negative K dt. Okay. You're going to integrate the left side from T0 equal to some final T. That's the right side. We can integrate the left side from, again, at T0, we have some initial concentration of reactant that we started with, and we're going to some final concentration, okay, whatever that might be. Might be 0, maybe it's not. Okay. So if we integrate the left-hand side, what is the integral of 1 over x, let's say? So in this case, 1 over the concentration of A. Natural log. This is going to be the natural log. 1 over x is the natural log of x as its integral. Okay, so this is natural log of A minus the natural log of A naught. Our initial concentration is going to be equal to negative K just times T. Let me just show our subtraction of 0. Okay. By properties of logs, I can rearrange this and write the concentration of A at time T over my initial concentration would be equal to negative KT. If I want to get out of natural log, I can raise it to e to the power. Natural logs drop out. And so I could, again, rearrange this to get everything just in terms of concentration of A, because this is what I ultimately want to plot. This is going to be equal to my initial concentration times e to the negative rate constant times time. And then I can plot this, okay? Again, I'm interested in actually looking or observing how the concentration of A is changing versus time. So I have time in seconds over here. I have whatever my reactant concentration is over here. Once again, I can let it start at 1. 1, 2, 3. So what is the shape of this curve going to look like, given that it's e to a negative power? Exponential decay. Thank you. Are you Caroline? Look, I'm learning people finally on the last day. It looks like exponential decay. So we have a couple different curves. Okay. So sort of same as before, lower rate constants, K, are going to have sort of a shallower decay. You're going to have sort of longer time points before you see absolutely no reactant in your forward direction. This is the direction of higher Ks. And you expect a shape that is exponential decay. This is not a line. Right? And so then again, the concentration of your product increases then exponentially with time.